Okay, so not surprisingly, we're getting into ones 5 and 6 groups. They're a little bit unusual molecules. So this first one, I guess, and the last one, both are noble gases, right? Xenon with some other stuff. And that always is like, what? It's a noble gas. It's fine. It's a real thing. It bonds. These things happen. So when you start to draw this, your only real choice is to take one of those pairs of electrons on xenon and use it to bond with the 2 fluorines, one electron from the pair to each fluorine, okay? So you're still left with 3 pairs on the xenon, non-bonding electrons, and then you have the 2 bonds. So 5 groups, 3 of which are lone pairs. So let's look at this in the simulation to make sure this kind of makes sense to us. Let's see, 1 less bond. Okay, so 5 groups, 2 of which are bonds, 3 lone pairs. Because the lone pairs need the most space, they will go in the plane where there's 120 degrees away. And then the atoms will go in the perpendicular region. So perpendicular from that plane, and so they end up directly across from each other. And I said 90, and it should be 180. Is that what you're going to call me out on?
Well, I was going to say, does it tell you specifically, like, the lone pairs or bonds on that website?
Does it tell me the lone pairs are?
Like the number of lone pairs?
Yeah, so you just have to, like, X them out. So like, okay, I have 2 bonds and I want 1, 2, 3 lone pairs. So you just click on, I guess you can't see me clicking. You just click on the lone pair to add as many as you want.
Oh,
yeah.
Okay.
Yeah. I just realized why that was confusing because I'm like sitting here going like this and like you can't tell what I'm doing. I'm just clicking on either the X to get rid of them or on the lone pair or the bond itself to add them in. And I said 90. This should be 180 because it's linear. There we go, just like that. Oh, no, I said 180. I don't know why I was thinking I wrote it down wrong. Oh, well. So these are ones that you're going to look at the chart that you're going to be given on the exam equation sheet that you need to understand how to draw the Lewis structure, obviously, but then you can use this to get you to the name. Yeah. No, because when we talk about angles, we're only talking about from one atom to another. And so, because we can't really define exactly where the lone pairs are. Now, technically in that example, it would be 90 from the lone pairs, but we don't care about that. We only care about 3 different atoms and how that angle lines up. Good question. Okay, so that was 5 groups, 2 bonds, 3 lone pairs. So that's how we know it's linear. Now, you have to use this to help you visualize them in 3 dimensions. So today we're going to talk about polarity of a molecule, and the only way there's all these little tips and tricks that people try to be like, oh, if there's a lone pair, it's polar. No, that's not always true. Oh, if there's different atoms, it's polar. Probably, but you got to make sure. Like there's all of these little nuances that make it impossible to just memorize some rule. You have to be able to picture the structure in 3 dimensions. And then we're going to talk about this idea of in the fight over the electrons, is there a clear winner or not? Okay, because that's what polarity really is are the electrons going to be evenly distributed or are they going to be unequally distributed? Now it's going to be within a molecule instead of just between 2 atoms like we talked about in chapter 10. Okay, so the only way to do that is to be able to picture it. So when you see the word seesaw, like, okay, you've now determined the molecular geometry, but do you know what that looks like? And are you going to be able to identify whether that's polar or not? So as we're going throughout it today, keep in mind that you still want to be tying this back to the simulation if you feel like you can't picture those shapes in your head clearly. Okay? All right, the next one was ClF3. Like I said, it's a little bit weird because we don't normally see chlorines like in the middle of a molecule. I might, on the exam, just to be perfectly clear, I might be like the chlorine or the underlined one or whatever, that's the central atom, okay? So when you do that, you know what, thinking about it, you couldn't even do the fluorine. Like even if you tried, you would end up trying and exceeding the octet and it would get really messy really quick. So that's how most of these are, is like I'm trying to save you the drama by telling you or by hinting at what's in the middle. Just draw what makes sense, right? Like if you've got 4 oxygens, the other thing is what's in the middle. If you've got 3 fluorines, the other thing is what's in the middle, okay? So we put the chlorine in the middle, it's got its 7 electrons, and then we have the fluorines, just like in the other one, you know, they need a single bond, so you just use 3 of those electrons, and you're left with 2 lone pairs on the chlorine. So we still have the 5 groups, but now 3 bonds and 2 lone pairs. So there we go, 3 bonds and 2 lone pairs. So this is T-shaped. That's the molecular geometry name because it is shaped like a T, okay? Now, these would be 90-degree angles. They're probably slightly less than 90 degrees. Now, I said this in the notes, and so I have to abide by it, but I said here, you will not be asked for the bond angles of these, like these guys over here. I'm not sure that it was that hard. Like, why did I say you don't have to know them? I don't know, but I already said it, so I can't take it back now. So just the ones that are labeled there. I'm not talking about, see, it says you will be given the names of the ones shown. You still have to know that this guy has 120 degrees and 90 degrees, that this guy has all 90-degree angles. I'm just not going to ask you, because those get weird, like, is it the 120 that's slightly less, or is it less than 120 and exactly 90? It just gets kind of messy. So that's why I'm not going to do those on the exam. On the homework, you probably will see some of those, and just like in this example. So this one's going to be slightly less than 90 because it's T-shaped, but then the lone pairs are going to squish it in just a smidge. Okay, next one, XeO4. I don't know why, but I really like this because it is an atypical tetrahedral. Like, we usually just think of tetrahedral as 4 bonds and that's it. It's just very straightforward. This one has 4 bond groups, but they're all double bonds. So I think that one's kind of fun. So you have to do this because oxygen's octet couldn't be satisfied otherwise. But you end up with xenon having 16 electrons around it. That is probably one of the highest that we see. So tetrahedral for both electron geometry and molecular geometry in 109.5. Okay, any questions on those? All good? Okay. So like I said, we're going to talk about molecular polarity today. Send this around as well. Just send it back and then come this way, and that'll simplify life instead of going across the aisle. Okay. So little bit of review from chapter 10 here with, like, I don't know if we introduced the idea of dipole moments in chapter 10. If we didn't, I don't know, I know we didn't in class. If it didn't introduce it in the book, we're going to talk about it now. But this slide is a review from chapter 10 because we're dealing with just 2 atoms and talking about, is there a difference in electronegativity that will create a difference in charge? So in both of these, we're trying to show HCl. This is the picture we were maybe most familiar with from the last chapter, where not only do we indicate which is positive and which is negative based on electronegativities. So remember, you can look up electronegativity values in your chart on the exam equation sheet. And I think we say hydrogen's 2.2. I always remember it as 2.1. I'm not sure what's on your equation sheet, but something around there. And then chlorine's 3.0. Okay, so these are electronegativity values. So the difference here, 0.8. So it's not huge, but it's a difference, okay? And what that does is it means that the negative charge is not going to be equally distributed. It's going to be spending more of its time on the chlorine because that is better at attracting electrons. So we were representing that with a partial negative symbol, and then on the less electronegative thing, partial positive. You can also see like the blob that's drawn there. There's got to be a better word for it. Well, there is, but we call it an electron cloud. I'm not sure why I don't use that, because maybe if I could just call it a cloud, at least that would be more consistent. So there's this fluffy cloud, and it spends more of its time over by the chlorine, okay, because that's better at attracting electrons. So a more formal way of representing this is with what's called a dipole moment. So this is a vector, which if you've taken a physics class before, you're probably familiar with this idea. A vector is a way to represent a difference in something and give it both an amount and a direction. So in the case of a dipole moment, we're saying there's a difference in charge, the chlorine being partially negative and the hydrogen being partially positive. And there's a certain amount that difference has. So we said the difference in electronegativity here is 0.8. If I were to do HF, this is actually a difference of, that's supposed to be an EN. This is actually a difference of about 1.8, okay? So a much bigger difference in electronegativity. So if we were to look at the dipole moment from HCl, which the dipole moment is this arrow, okay? It has a positive side here that's on the side that's partially positive, and then it points towards the side that's partially negative. So the direction of it, like the fact that it's lined up with the bond, that's important. We wouldn't draw it like up and down because it needs to be pointing from the negative thing to the positive thing. And then the size of it tells us about how big that difference in charge is. So for the HCl, maybe that's it. For the HF, maybe it's like this, okay? So it's the bigger arrow represents a bigger difference in electronegativity, or what will result in a bigger difference in charge. Sometimes I'll also draw these as like, this one has a partial negative and a partial positive, and then like to emphasize the point, I'll be like, this one has a big partial negative and a big partial positive, okay? Just physically drawing the partial sign bigger. So a more formal way to do that is by drawing the arrow of the dipole moment bigger. Okay, so a size and a charge associated, or not charge, sorry, a size and a direction associated with this arrow to represent the difference in charge. Okay, what I want you guys to think of, I'm like 20 years in, I'm still like perfecting how to explain this. So what I want you to think of when you think of polarity, like a polar bond in this case, is I want you to think of, in the fight for the electrons, is there a clear winner? Okay? In the fight for the electrons here, the chlorine is a clear winner. So we would say that the molecule HCl is polar. That's how we describe it. Think polar like it has two poles, a positive and a negative pole, P-O-L-E, like North Pole, South Pole. But these are poles like charge poles. So negative pole, positive pole, okay? So we would say that these molecules are polar. Now, up till this point, we've just talked about polar bonds. Since HCl is a real molecule, I can say the molecule is also polar. But what happens when I get more more complicated molecules that have 3 or 4, 6 atoms. Okay? So let's look at, I'm going to come back to this. Let's look at CO2. And just to start, let's just look at this half. Okay? So it's a CO bond. There's a difference in electronegativity of 1 unit, CNO, yes. So the difference in electronegativity, if you go look it up, C is 2.5, O is 3.5, okay? So there's a certain amount of size associated with the vector, the dipole moment. I should just call it a dipole moment. I just want to connect it to physics if you guys are familiar with that. And it's starting on the positive, on the carbon side, and pointing towards the oxygen, okay? So that is the polar bond. So this is still a polar bond because it's a bond where there's a difference in electronegativity between the 2 atoms. Okay, so the electrons are more attracted to the oxygen. We could also do like the partial negative thing. So I could put like a partial negative there and a partial positive there. Just drawing it on the other one so I don't put too much stuff on my one I'm working on. Okay, the difference here is that there's also another polar bond, right? There's another CO bond that has a difference in electronegativity, and it's the same atoms, right? So the difference in electronegativity is still 1. So the size of the arrow is the same, but it's in the opposite direction. So what happens here, so go back to our idea of is there a clear winner, okay? You've got the carbon in the middle and the 2 oxygens that are both just as strong on the outsides, and so they're both pulling in equal opposite directions. There's no clear winner for those electrons, right? Some are being pulled this way and some are being pulled that way, but there's no clear winner, okay? So even though there's 2 polar bonds here, they will cancel each other out and make the molecule nonpolar. So I think it's important to like say it clearly and put it in words so that it's in your notes in words because it mixes people up. If you have polar bonds, which we do, if they are oriented in a way that allows them to cancel each other out, then we would say that the molecule is nonpolar. So it's fine that they have polar bonds, but they're oriented such that they can cancel each other out completely. So I guess we'll have to talk about this in 2 different ways. We'll talk about it in terms of do the things cancel each other out? When the molecules get more complicated, it can be hard to see. Like in this case, obviously they cancel each other out because they're directly across from each other. Let's look at the previous slide, example 3. So if we actually gave those numbers, so think of like an XY coordinate. Okay, so here's 0. And this vector is going this direction, so positive, and it has a certain quantity associated with it, 5. And then one's going negative, and it has 5. If you try to add those 2 together, they just cancel each other out, right? There's an overall 0. This is a thing, like in physics, you'll add vectors together. If I had one, though, that was like positive 5 in the y direction and positive 5 in the x direction, those don't cancel each other out, right? Even if it was negative 5 in the y direction. Let's do that because that's more similar. Okay? Even if it's positive and negative, same quantity, if they're not in equal and opposite directions, then it's not going to cancel out. Okay? So this is a great example of maybe it's a little bit hard to see that they don't cancel each other out. We're going to rely on this idea of a competition or a tug of war, which is what we explained polarity as originally, and say if I have an atom in the middle and I have two things pulling, they're both the same strength and they're pulling in equal opposite directions, but they're at an angle like this, then they're still going to move me, right? The molecule's still going to shift if they're pulling downwards. Whereas if they're pulling straight out, they kind of oppose each other and cancel each other out, right? Their efforts are canceled out by the other one. Okay, so we're going to keep going back to this tug of war example to know, are they canceling each other out? So I'm going to put here, cancel out, think, tug. Is it tug o war? Tug of, it should be tug of war, but as I'm writing it, I'm thinking it's like tug o war. Someone can Google that if they want. So if there's no clear winner in the tug of war, that means that they canceled each other out. Okay, let's look at, I always hate this example. I need to think, I need a periodic table. Wait, no, I can do this. Okay. I want a better one than that. Okay, this isn't perfect. So if you go look at the numbers, don't get mad at me later. Okay. What about a molecule that's also linear? Okay, they're directly across from each other, but they're different atoms. So the CH has a very tiny difference in electronegativity, whereas the CN's difference is still small, but a little bit bigger. Okay, so the numbers don't match up exactly. But let's pretend that it's 5 and 10 just to make our lives a little simpler. Okay, they're different. That's the point. And I could put another atom over there. I guess I could put like, I don't know. I could put like nitrogen over here and fluorine over there or something. Okay, let's do that. It's not like I actually am worried that you guys are going to go call me out on it and be like, I looked up those electronegativity values and that doesn't make any sense. But just in case, I want to give good examples. Okay, so we still have two polar bonds. One is very polar and one is just a little bit polar. Okay, so they're in opposite directions, but this one's really big and this one's not as big. Okay, those do not cancel each other out to equal 0, even though they're opposite, because their values are so different. Okay, so they have to have the same value and opposite directions to fully cancel each other out. So the example in 3 was CO2, and that would be nonpolar. In example 2, NCF would be polar. And think of the tug of war, okay? Fluorine has an electronegativity of 4. Nitrogen has an electronegativity of 3. So if I'm carbon in the middle, and I've got fluorine over here that's really, really strong, and the tug of war starts, obviously there's a winner over here, right? The fluorine is better at attracting those electrons, and it's going to win the tug of war. So if there's a clear winner in the tug of war, then we would say that it's polar. I feel like I'm going to have to summarize that one more time in like text, but that's okay. All right, let's do another example. So most common example you'll ever hear of a polar molecule, water. Okay, so differences in electronegativity, let's start there. Oxygen is 3.5 and hydrogen's like 2.1 or 2.2. And so the difference in electronegativity is 1.3. And that's for this bond as well as for the other one, right? They have the same difference in electronegativity because it's the same two atoms. This time though, because there's those lone pairs, remember water looks like this. And really, let's remember what it looks like three-dimensionally, because like I said, you're going to have to be picturing this for it to make sense. Okay, it looks like that. The lone pairs are kind of lined up. The bonds are kind of lined up. And so when you look at this, the oxygen is the strong thing here, and the two hydrogens, and the oxygen is not being offset by those hydrogens, right? Because it is much stronger, and it's not like a clear resistance from both directions. It is, the tug of war is like one-sided, okay? So there's going to be a clear winner there. There's going to be a shift in the molecule during that tug of war. It's another way you could think of it. And so this molecule would be considered polar. So we've got polar bonds. They're equal in size, but not direction. They're not equal, they're not opposite in their direction, but not opposite in direction. So because of that, the molecule is then polar. And just to be really clear, when we say they're not opposite in direction, so that means they cannot cancel out those two dipole moments. Or in the tug of war example, you would still have a winner in the tug of war. Okay, you can, just like we did here, there, you can do this for things that are in the X and Y. So I'm going to show it. You do not have to know what I'm doing or care about what I'm doing, okay? If you really like math, this might be helpful to understanding how they cancel out. If not, just leave it, okay? So in a vector that's at an angle that's not exactly in the X or the Y direction, we talk about it as having components in the X and the Y. So maybe here it's like this would be positive 5 in the X and positive 5 in the Y. And then on this side, it would be negative 5 because it's pointed towards the negative, negative 5 in the X and positive 5 in the Y. So there are certain components, the X component of that vector would cancel out, but not the Y component. And what this dotted one is showing us is like the sum of the two. So if we added those two vectors together, we would get something that is exactly along the y-axis, and it's twice as long as those vectors are. Well, at least that their y components are. Okay? And you'll notice when we add those, it's still pointing towards the negative thing, and its positive side is towards the positive thing, because we said water is partial positive, and the hydrogens in water are partial positive, and the oxygen is partial negative. Okay? That's another way that you know that there is molecular polarity, is if you have those partial charges still exist and they're not balanced out or canceled out, then the molecule itself will behave like it's polar. Okay, so two ways we can approach this, and I think I'm going to do what I did in my other class. I was going to just go through all of the Lewis structures we'd drawn previously and say, is it polar or nonpolar? Is it polar or nonpolar? I think what I'd rather do is we're going to use this chart here as like example molecules and go through each one of these and say, is it polar or nonpolar? So I can give you a couple, like I'll probably write in the formula of one that we've done that looks like these. So like CO2 we said here, BCl3 we did there. I think we did SO2 for this one. So I'm just going to write these in. So if you want to reference back to the pictures that we've done of these, each of these individual ones, you can. Ooh, I don't know if I'll have one for all of these. PCl5, I think. We did do a seesaw one. What was it? SF4? It was SF4. We just did a T-shaped one, CLF3, and we did a linear one, but yeah, it was this, XEF2. And then SF6. Ooh, I know we haven't done one of those. I'll have to find us one of those. I don't know that we've done any of these ones. Okay, let me get a couple examples. Okay, this one here, there are all these random xenon compounds. It's kind of funny. IF5, so like good practice, good studying. These ones that we haven't done, go ahead and draw them out for yourself and prove that they are what I'm saying they are. And I'm going to have to verify these other two because I don't trust the internet enough. That's where we've gotten. It gives us a lot more answers, but we can't be quite as trusting of them. Okay, so what I want to do is we're going to go through each one of these and we're going to we're going to do the simulation and look at it and decide, is it polar or not? Now, a quick caveat before I say this. Before we do this, you'll notice that in every single one of these, there's a central atom, and then there's all the atoms that are around the outside are the same. Okay, so I specifically gave you CCl4, not CCl2F2. Just like we showed in this example here, if you have different atoms on the exterior, it's almost certainly going to be polar. They have to be the same atom, the same electronegativity in order to cancel out. So we're only talking about the examples here where the external atoms are the same, and then we're going to decide is the molecule polar or not. If the external atoms are different, 95% of the time it's going to be polar. It would only not be as if they had exactly the same electronegativity. Okay? So being really clear that when we go through this chart, like when it says X, A is the central atom and X is the exterior one, they're all X, right? They're all chlorines, or they're all fluorines, or they're all hydrogens. They're not different atoms, because that's going to change our answer. Okay, so I don't think we need to do CO2 because we just showed that one. We said that was non-polar, so I'm just going to write NP. And remember, NP means polar bonds cancel out. Or in the tug of war analogy, no winner in tug of war. Okay? Polar would mean they don't cancel, or there is a winner. Okay, so moving on to the second row, BCl3 and then SO2. So I'm going to open up the simulation. And what we might be able to do in this case, it's close enough, we can actually use the real ones, the real molecules. So if you're going through this on your own, and this might give us the last two examples too, you can use the real molecules if you want. Okay, so this says it's BF3. It's going to look the exact same as BCl3. Okay, now those aren't exactly across from each other, right? But they're three things all equally spaced. So think of the tug of war. If all three of these are chlorines, is there a clear winner? No, they all pull in such a way that it's very balanced, and so no one is a clear winner in that tug of war. What that means is that those polar bonds are canceling each other out. They're canceling them out in the X and the Y direction, but the way you can visualize that is with the tug of war thing. So we would say that this is non-polar. Did I say this? I said this already about North and South Pole, right? That's what we mean when we say polar. We mean like there's a side. There's a positive and negative side, okay? So if they cancel each other out, that means there's no positive and negative side. If they're not canceled out, or if there's a clear winner, that means there is a positive pole and a negative pole. All right, SO2. Oh, what just happened? I think I lost my notes. We'll find them. Okay, SO2, this is what SO2 looks like. So really similar to water. It's like the trigonal planar, but now one of those things is a lone pair. So the lone pair doesn't exhibit any electronegativity, because why would it attract electrons? It is electrons, right? So we've got those oxygens, and they're pulling on those electrons, and they're uninhibited by anything on the other side, okay? So in the 3, there's nothing on the opposite side to cause that to be an issue. This is my kid's school, is why it's ringing through, so. This is Carrie. Uh-huh, is it Luke? Oh, at the middle school. Oh, okay. 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 What is the, like, what is the policy? I have another class to teach until noon. Like, could I let her rest there for an hour and a half and come get her at like 12:15? Okay, perfect. Yeah, tell her to try to rest, and I'll be there about 12:15. Okay, thank you. Bye. That was so funny, because I had one kid this morning who's like, my stomach hurts, Mom. I'm like, if it gets worse, go to the nurse. So, of course, I assumed. And then she's like, oh, the middle school. Just kidding. It's the other child. So I can tell we're going to have a really fun weekend. All right. So SO2, because of that lone pair, it's offset in such a way that it would be polar. Okay? I'm not sure what keeps happening there. So this guy would be polar. All right? Now, I'm going to give you a hint. This is not a 100% answer, but whenever you have these kind of original geometries, the ones that have all bonds, those are always nonpolar, assuming all the external atoms are the same. Okay? There's a caveat, so wait for it. This does not mean that just because there's a lone pair, it's polar. So we're going to look at those examples next. So I'm going to highlight them to be very clear. This, and this, okay? I'm going to show you these examples, and I think you'll see really quickly why they are still nonpolar, even though there's a lone pair there, that you would think is like offsetting the geometry. Okay? Okay, so XEF2. So even though you have those lone pairs, like we looked at before, we drew this one before, they're in that plane and the atoms are still exactly opposite each other. Okay, so they cancel out, so it would be nonpolar. XEF4, very similar, but now you've got 4 in that plane. Well, you've got 2 straight across, and then these 2 straight across. Okay, so they're all able to cancel each other out, even though there's those lone pairs. And then the last example is actually also linear. Of course, they don't have one here, so I'll have to click back over here. And it looks like this. It's just got 4 electrons in that plane and then the 2 atoms directly across. Okay? Now, if you go through and look at every single other one of these that's not highlighted and not blocked out, the lone pair in each of those instances is, you could kind of think of it as it's not symmetrical, okay? If you have that symmetry there, then those bonds can cancel each other out. Usually what happens with lone pairs is they offset that symmetry so that the bonds are not able to cancel each other out, okay? So all of these ones end up being polar. Now, if you try to go through and just memorize this on the table, maybe you'll be okay. Probably not the best way to do it, probably not the best use of your brain. Also, recognize that this is only when the external atoms are the same. If I swap out one of those fluorines for a chlorine, that's going to totally make the story different. That would then be polar, even if I said it was nonpolar before. Okay? So what I want you to do this weekend is Chapter 11 homework. I want you to do as much of it as you can, meaning any question that asks you about molecular geometry, electron geometry, angles, and polarity, all of those you can do. The only thing you can't do, and what we'll cover on Monday, did I say that already? Remember, it's a remote class, so Monday being a video. We're going to talk about hybridization, which is the orbitals that happen in these molecules. So it's very different than what we've been doing. So try to do as much as you can on the homework this weekend so that you just have that one additional concept to cover on Monday. Okay? All right, I will see you guys. Well, I'll see you on a video then, and then I'll see you on Wednesday and we'll do review.